Okay, sorry about the delay for the setup. I'm going to talk about limits to text encoding. The question is, are there any limits to text encoding? And if you, well, unfortunately I wasn't here yesterday for Florian Kulma's talk, but he talked about the most beautiful writing system. And another question is the most difficult writing system of the world. And so one of the basic question that I'm asking in this talk can be kind of changed, transposed to this question. And my answer would be there are no difficult writing systems. That might surprise you a little bit. I would say there are not anymore any difficult writing systems. And, well, let's see whether you can agree with me or not, and how far. Okay, so the question, are there any limits to text encoding? There are no limits to text encoding anymore. So this is the outline of my talk. I'll talk about formal limits to text encoding. I'll show the wide variety of text encoding mechanisms that are currently in use. Talk a little bit about surrounding technologies and limitations, and then the conclusions. I was already told that I'm in Japan, working on software internationalization, World Wide Web architecture, and programming languages. I'm still involved in the W3C. I'm also involved in the Unicode and Internationalization Conference. And I'm a Unicode individual member. Actually, since this year, I'm a lifetime member, because now if you're a member for 10 years, you get upgraded to a lifetime member, which means you don't have to pay any dues anymore, which saves the hassle of thinking, meeting the deadlines and stuff. I also want to point out that I'm not a linguist, so if there's any problem with terminology or so, it's probably just my fault, and just nicely pointed out to me. It's not, I didn't do it on purpose. Okay, my approach is, well, focusing on encoding, not writing. I'll show the relationship a bit in a bit. I'm mostly focusing on technology more than on theory. I hope I still can find some theoretical aspects. And, well, technology is often boring because hopefully it just works. You often just see it when it's not, or you realize that it's there when it's not working. Okay, let's look at the relationship between encoding and writing. Encoding is a substrate for writing with present-day technology that has been pointed out in the previous two talks. If you want to write on a computer or whatever, you need to encode it, the text. A little bit wider, we can also look at encoding and the surrounding technologies as a medium for writing, similar to the tortoise shells and paper and brush that we heard about yesterday. So there the question came up, how does the writing system change with these changes, and how does it change when we move to electronic encoding? It's needless to say that research on writing, gʁafematik and so is crucial for good encoding, but there are also some places where encoding might influence thinking about writing. A general model here is that we have ideas, speech, writing, and encoding. Encoding is at the bottom here. Below that, there's some physical stuff like electrons or whatever. The units here are for ideas. This is more a cloudy thing, yeah. In speech we have things like phonemes. In writing we have graphemes. In encoding we have just code points. It's basically, think about them as numbers. Then we have flexibility. Ideas are very flexible, yeah. You're often not exactly sure what you're thinking about before you get to talk about it or write it down. Speech is still fluid. Writing is somewhat fluid. It gets kind of more fixed. And encoding is very strict. Yannis has also just explained that, well, once it's encoded, it cannot be changed. There's very few instances where changes have been made, and they have met with very big backlash, and the Unicode Consortium won't do that anymore. They just leave, if necessary, they leave something there and do another encoding. It's just left on the as garbage. There's no garbage collection. So how can encoding influence thinking about writing? For example, Greek and Coptic, are these two scripts or one? For a long time, Unicode has been of the opinion that these are one script. Later, they changed it to two scripts. Bengali and Assamese, the position is currently and will probably stay that they are the same script. Maybe Unicode defines an alternative script name or so just to make the Assamese a bit more happy, because they are not happy about the fact that the script is called Bengali and not Assamese. Also related to Professor Kulma's talk yesterday, well, is this a syllabic script or an alphabetic script? Actually, here the answer by Unicode is that it's both, because it's so well designed. It was encoded about 3 or 4 times in Unicode, and at least 3 of these encodings are still left there. Another example is Georgian Mtavruli. Let me show the example here. This is this is the standard Georgian script, and this is this Mtavruli. This is something like an uppercase. It's not exactly used the same way as uppercase, but it was until very recently it was just treated as or it had to be treated as a style variant. A style variant like you would select italic when you write the document. But now it has been encoded in Unicode 11, so this changes it to uppercase variant of the lowercase on the left side. Also for individuals letters, we just heard the case of the uppercase German sharp S. Actually, it wasn't created by Unicode. Unicode was resisting it, and only when examples of actual street signs and actually even an edition of the Duden that had it on the front page, was found, Unicode had said, okay, we have evidence that this letter exists and we encode it. But you see that the encoding doesn't preclude further research. It doesn't preclude that you come to a different conclusion. You can still say, well, the Georgian Tavruli is just a style variant. It's not really uppercase, but the baseline assumptions and the terminology are kind of might be dominated by the encoding. So here, this is what we just have a look at. Okay, then, well, you all probably, well, if you're not too young, then you have heard things like this, like we have to abolish lowercase because computer cannot handle it. Uppercase is enough, or Chinese Japanese has to be written with Latin letters, and so on. But this was a long time ago. There were many different encoding limitations, like the number of code points. We heard about Malayalam yesterday that, well, 256 was just a limit that somehow they had to deal with. Writing direction, reordering of letters, character variants, all kinds of encoding limitations existed. And these limitations existed in the encoding itself, but also in the surrounding technology. Like fixed code point to glyph mapping, that was a thing that was for a very long time, that was just built into technology and had to be overcome. It's interesting to see that if you remove limitations, because you need to remove them for some scripts, for example, ligatures are to some extent necessary in Arabic, they're necessary in Indic scripts, then you also get the same technology for other scripts. You can then do ligatures in Latin where they're not so, well, if you really have a nicely printed book, they're very desirable, but they're not really necessary to read your email. Yeah. So now I'm coming to the main part of my talk, the encoding mechanisms. Here's just a list. I'll go through this in a little bit of detail. So what the number of code points, there were 5-bit codes on paper tapes, 6-bit, 7-bit, and 8-bit. Unicode was initially 16-bit, which is 65,000 and something code points, but it was extended to 1,000,000 and a bit of code points, and currently about 130-something thousand code points are used, which is about a bit over 12%. And additions are a few hundred to a few thousand per year, of which emoji is maybe 50 or a little bit more. One encoding mechanism that is very well known is combining diacritics. Actually, it already existed in ASCII. It has kind of been forgotten because we have better stuff now. But characters like this, the hat, they were actually designed to also serve as diacritics. And you would use them with a backspace. And in emoji, we could speak about things like gender, skin colors and hair colors and whatnot. I'm not sure what the newest fashion is. I'm not really an emoji user, I have to admit. But we could also think about them as diacritics. Then the next thing is joiners. There's the zero-if joiner and the zero-if non-joiner. They are useful in usually connected scripts like Arabic, Indic, and Indic. For example, in Arabic, you can show a connected form alone by using a zero-if joiner. Just tell me, well, there would be a character close to you to connect to, but they are also now used in emoji. For example, here we have a character which is kiss, woman, man. Note that the woman is first, but then the man is on the left side. I'm not sure. Maybe that's also a problem of whatever equality. You can see the various special characters connected here with these serif joiners that to say this should all be seen as a unit and somehow displayed together. And the serif non-joiner does the other thing. I can show an example here of Malayalam. Maybe I should. Here there are different variations of writing a combination, and these variations can be selected with serif joiners and serif non-joiners. For example, we have virama, serif non-joiner, serif joiner virama, and then serif non-joiner virama, which is the just this one reversed. So then next we have variant selectors. They are a postfix code to indicate the glyph variation. They are both standard variants and registered variants. They are used. They were first developed for Mongolian. They're used for Chinese and Japanese and mathematical symbols and all kinds of things, and then also for emoji. Let's have a look at some examples. Here is a page by done with a lot of careful work by Richard Ishida. This is a Mongolian character. This should actually be turned. You see it, it's a different direction. How much time? 10 minutes. Okay. So what these variants refer to is here. You have isolate, initial, medial, and final. We know this from Arabic, so this is not something very surprising. But then we have these variants here. And I'm still not sure whether I understand this Mongolian script correct, but at one point I was kind of thinking that it's actually, well, if you would apply the way this is done, it would be like you would, for English, you would use Shavian or another phonemic encoding, and then you would add variant selectors so that actually in the display you get the letters that we are all used to, yeah? It sounds crazy, but it probably is, and there's actually work going on to rethink this, and maybe this will all change. And then let me see. Yes, then this is the variant selectors for CJK, for example. This is Mongolian letters, this is Myanmar letters have variant selectors, and so on. These are standard variant selectors, and then this is there's a registry for kanji or hanja, where different forms of letters, for example, here you can see these diagonal strokes go one way, and here they go the other way. And this is the same character in the sense that it has the same meaning, the same pronunciation, the same usage, and in general, people don't really care too much. It's maybe depends on the font, on how this might look, but then there are situations like names where people really kind of insist on getting one version or the other. And then this is done with these variant selectors like this E0102 and the big. Well, that's a bit. We can probably blow this up a bit here. Sorry about the small one. Okay, then what's next? Oh, no, this is a separate issue. Okay. Then we have sequences, for example, there are flag sequences. They are sequences of two characters that are equivalent to plain Latin characters. And the way it works, you take the F flag character and the R flag character and put them together, and then you get a country code, and then the country code determines that this is the flag of France. So you see it gets more and more complicated. It gets even more complicated when we get to the flag of Wales. Why is the flag of Wales here? Because we just started the Soccer World Cup, and in soccer, the UK is not a country. There's England, Wales, and Scotland. So they needed to, suddenly some companies found out that they needed to have flags for these three soccer countries, and they came up with another way of encoding them. And if you look at this, this is actually 28 bytes. Yeah? The KISS, I didn't calculate the KISS, it's a little bit more irregular, but this is 28 bytes in all these encodings. So it's a single, on what you see is a single character, but in terms of encoding, it's quite a complicated construction. And then something that is only just under development is Egyptian quadrants. This is a very beautiful thing. Let me see. The things like that. Egyptian hieroglyphs combined into squares. And there is now discussion how to encode these, and you would also get sequences like this and operators. Here is the list of operators. Yeah, and you need parentheses and stuff like that, so you get the nested structure. But you already have that in the BIDA algorithm, so it's not really something new. And you can always claim that you have a limited number of levels, so it's still regular, if you want to claim it's regular. Okay. This encoding the more complex it gets, the more important it is that you have some input technology that helps it. The input was originally limited by the keyboard, you know, the number of keys and the number of shift keys you had. But for Japanese and Chinese front-end processors, or so-called IMEs, were developed that you input phonetically and then you can select your characters. And that was more than on smartphones adapted, and predictive input was also added, so you can type faster than you can than maybe on a typewriter, because it tells you what you should type or what you should input, which as has been shown today it might be a good thing, or it might be just lead you into a certain direction. And okay, then rendering technology is also very important, because if you can not show things, then it's not really gʁafematik. So here's another example of variant selectors. For example, the snowman has a text style and an emoji style. The text style is just black and white. The emoji style is maybe with yellow or orange nose, carrot, and things like that. And actually, the interesting thing is that the snowman was in Unicode 1.1, which is something like 1993. So emoji were in Unicode very, very early. We just didn't know it. Yeah. And this is a Wales tax. So what I'm showing here is, this is difficult to interpret if you don't know these people, but these are actually representatives from the open source community, from Microsoft, Adobe, and Apple, introducing at a type conference, A-Type I, open type font variations. This is a technology that Thus, in 2016, or, well, when it's actually used, it will probably be a little bit later, but does what Metafont did a long time ago, and what Adobe Multiple Masters also tried to do. The difference here is that whether this technology and to what extent it will be successful, it shows that different from earlier days, the different companies that work on rendering technology work together much more than they did. And this is important because it makes this font technology, if you have only one way to encode fonts, which we are not yet completely there, but it makes it easier to encode new scripts because it makes it easier to show them and implement them quickly. And the same for web fonts, which in the old days there was a Microsoft system for doing web fonts and a Netscape system for web fonts, and nobody did web fonts. And now there's a single WOF format and people are doing web fonts. This is something about emoji. These are just pragmatic positive points for emoji. There are lots of others, yeah. The emoji actually help getting encoding mechanisms implemented, yeah. I have made that experience myself. If there's something, well, for a very rare script, then people don't really care, but when they realize, oh, this is actually needed for emoji, then it gets done, yeah. And it helps getting new versions of Unicode implemented and deployed quickly. Yeah? People want their emojis, so they're up. Smartphone makers and so have to make sure that they are up to a new version. They also help collect donations for encoding research, and they help get publicity for Unicode and encoding issues. Of course, this encoding thing is not, it's not only, there's still some problems. There's still, well, this is quite, why is this here? This is an example of Myanmar, where they still have encoding problems because there was a hijacking of Unicode by some other, with some other encoding. There's also some rendering limitations. There's still, mainly in the Microsoft stack, there's still this shaping engine in the middle between the encoding and the font. And so you have a three-step process. Even if the encoding, the script is defined, you have to define the shaping behavior before you can actually create fonts. And then there's also the chicken and the egg issue, which is if you want to have some new characters, some new script, Unicode will not say, okay, you have a great idea, we'll just encode it. Yeah, you should just first you show actual use, like with the sharp S that I explained, and this kind of can be difficult because use means use with encoded use and so on. Okay, here are my conclusions. You have seen there's a large variety of encoding mechanisms devices, and I basically say, well, there's you have seen so many different things. I hope that I was able to show you that, well, it's really not, if some new script comes with some different requirements, sure, we can handle it. We have already handled all these very weird combinations of code points and to letters and so. So there's not really any technical limitations to encoding anymore. But interactions between gʁafematik and encoding are definitely something that is very interesting for the future to study. Thank you.